So in the last video, we constructed the moduli space of smooth cubic surfaces U, which was an open subset of P19. And on this P19, we had these coordinates, C alpha, where alpha is basically just one exponent of a degree 3 monomial. So it's an element of n to the 4 such that the sum of the entries is 3. And then for such a coefficient vector, we get Fc, which is just the corresponding polynomial of degree 3. And then the associated cubic surface is just the vanishing locus of this homogeneous polynomial. And next, we talk about these lines on the cubic surface. So somehow what we're really interested in the theory. And the crucial geometric construction that helps us with this is a so-called incidence correspondence. So in general, this term incidence correspondence can describe that you have a moduli space which doesn't just parameterize a single geometric object like a cubic surface, but parameterizes, for example, a pair of objects which have some relation to each other. And in this case, well, we're interested in cubic surfaces and we're interested in lines lying on them. And so we write down this moduli space M, which, as I said, is just a pair of X, a cubic surface, and L, a line in P3, which we know is described by this Grassmannian G2, 4. And then this pair is contained in M if this L is actually contained in X, exactly what we're interested in. Okay. And this a priori is just a subset here. And we have a map from M to U, which is just a projection on the first vector. So we just remember the cubic surface X. And then, of course, what we can immediately see is that if you have a point in U, so an X, then the fiber of this map P is exactly the set of lines L which lie in X. So that's the thing we're interested in. So basically, we want to show that any point here has exactly 27 pre-images. And the crucial technical lemma that will help us to conclude this is, first of all, that this M inside this product here is closed in the Zariski topology. So it's actually defined by some algebraic equations. And secondly, that the picture that we should have in mind is basically a picture like this. So somehow locally, if you are on some point, let's say even on U cross G2, 4, or maybe a point in M, like here, if you are anywhere here, then locally in the classical topology, like in the complex topology, M is the graph of a continuous and differentiable function from U to G2, 4. So in other words, any point here, we're basically in a small open neighborhood, we are a function like this. Or the graph of a function like this. Okay, and so this we want to show, and then we're going to see in the next video how this helps us. And so for the first part, so we need to say that this M is described by some algebraic equations, essentially. And being closed can be checked on an open cover, and we check it on this nice open cover of the Grassmannian that we have already seen, because we have seen that it's covered by these affine patches. And so in particular, if you look at the locus where the first kind of minor of this matrix is non-zero, then you can get this into this the standard form of the identity matrix, and then the remaining coordinates are exactly affine coordinates on this patch U0. So somehow this is a 4-dimensional space with these coordinates. And then, well, so we covered this, and then we have if we want to cover this whole thing here, then it's covered by this curly U cross the U0. So in other words, the coordinates on here are these coefficients C alpha, and then these A2, A3, B2, B3 on this patch U0. Okay, and then we write down, well, what does it mean that that this point here lies in M? Well, it means that if we take the defining function, so fc is the defining function of the surface X, and then we want that the line L is contained in it. And the line L is parametrized. We have seen this a couple of times, just by s times this vector plus t times this vector. So somehow just s times the vector 1, 0, a2, a3 plus t times the vector 0, 1, b2, b3. And so this should be 0 because all of these points should be contained in the surface X. And this should happen for all s and t. So this should be an equality, which is essentially an equality of polynomials in St. Okay, and so now, well, we can expand this. We know that Fc, this was here, so somehow Fc is just this sum here, and we can basically just plug it in. So plugging in this summation, we sum over alpha, then we have C alpha, and then we have the different coordinates of this summation here to the correct powers. And so we see, for example, the first coordinate is just s times 1 plus 0 times t. So it's just s to the power alpha 1. Second coordinate is t. We raise it to the power alpha 2. So here we just plug in this monomial, x1 to the alpha 1, x2 to the alpha 2, and so on. And then the remaining terms are s times a2 plus t times b2. And the last component of the vector is s times a3 plus t times b3. And this should be 0 for all st. Okay. And so we won't spell this out now, but we at least give some, I mean, we can at least imagine that we spell, I mean, we multiply these things out. And then we see, I mean, we get a polynomial. We can interpret this as a polynomial in S and T, whose coefficients are some expressions in these C alphas and the A2, B2, and so on. So we can spell this out as a polynomial from I equals 0 to 3 of S to the I, T to the 3 minus I, because we see, I mean, the sum of these alphas is 3, and so this is homogeneous of degree 3 in S and T. And then we get some coefficient. We just collect everything that is associated to this monomial, and this will depend on the C alphas. It will depend on the A's and the B's. And so this should be 0 for all ST. But now this polynomial vanishes for all S and T if and only if all of these coefficients will vanish, right? So for I equals 0 up to 3. And now, well, we see we started with the condition that this is a point in M, and now we have just a polynomial in these coordinates. And so this cuts out a closed condition. So this is closed in U cross U0. And this is what we wanted to show. We wanted to show that M is closed in circular topology, so it's cut out by some conditions. And this has worked. Okay. Then the next part, we want to show locally in the classical topology, this is the graph of such a continuous function. And the first thing that we want to argue is that we can again place ourselves in some nice situation. So we can go to some nice point on this M. In particular, since we already did the analysis here on this patch, maybe we can move things around so that we are actually in this patch. And this indeed works because we have seen already that on this P3 in which everything happens, that's the ambient space, we have an action of this group PGL4 by projective automorphisms. And then this action here actually induces an action both on M and on U, because somehow, well, if you have such a pair of a cubic surface in P3 and a line in P3, such that L is contained in X, then you can act by such an element of this PGL2 just by moving both the surface and line lying on it. You just move it around. You just apply this automorphism and you still get a cubic surface, you still get a line. And so this defines a well-defined action. And then this map P, if you also act just downstairs on the cubic surface by just moving it around, then this becomes an equivariant map. And then whatever you want to show about any point being some locally a graph here, well, this is a property which is still true after you move things around. And so you can basically, if you want to check it for one point, you can check it for any point in the orbit. And in particular, we can, this means if we are given any point in M, we want to check that it's locally a graph around there. We can take an element G in G such that it moves this line to our favorite line in P3, because you can see, I mean, these were basically invertible matrices. So this is basically like a change of basis in k to the 4, because P3 is like k to the 4 minus the origin up to scaling. And so this line spanned by two vectors, you just move these two vectors to the vectors, let's say the first two E1 and E2, the first two standard basis vectors. And so we can move this line around until it is exactly this line here, which we see as an element of this G24. And then this line here is contained in the U0, where we did the analysis before, because it is just the row span of this matrix. When you set all of these entries to 0, then you get the first and the second standard basis vector. So we have moved ourselves essentially in these local coordinates here. We can move ourselves to the place where A and B are actually 0. And that's always nice to nice for calculations. Okay, and then so after this shift, we are now exactly at this point, and then we want to show at this point the function is locally a graph. And so what we now see is that well, over the if you fix a point in curl U, if you fix a cubic surface, then the remaining coordinates are this patch U0, which is isomorphic to A4, given by these 4 variables. So it's a 4-dimensional space a priori. And then the space that we care about, where we want to show it's locally a graph, this is cut out by 4 equations, right? These were these Fi equals 0 at these points. So you have 4 variables and 4 equations. And you know that you're currently at the solution point when you set all of the coordinates to be 0. And then it's just the standard implicit function theorem from analysis, which says it suffices to check that that this Jacobian matrix, which takes the derivatives of all of the all of the 4 defining equations by the 4 variables. If this is invertible at a equals b equals 0, then you are locally a graph like this. So somehow this is what we reminded ourselves a couple of videos ago, that this is the interpretation in terms of the implicit function theorem. If this matrix here has rank exactly equal to the number of equations, then you're locally a graph in this way. Okay, so we have now reduced our problem to a purely algebraic problem. We just take a matrix and we want to show it's invertible. And so let's start computing this matrix. And so we begin by taking the derivative with respect to A2. This is like the first column of this matrix. So we take the derivative d by dA2. And now, well, now we would have to say of f0, of f1, of f2, and so on. But in fact, we can do all of them at the same time in the following neat way, because we just kind of reverse what we did before. We had the sum I equals 0 to 3 of s to the I, t to the 3 minus I of f big I, f I like this. And then if we want to have the ith row of this matrix, now we just take the coefficient of s to the I, t to the 3 minus I. And we want to evaluate this derivative at a equals b equals 0. And the good thing by writing it like this is then we can see we got this expression by expanding this fc. So now we reverse the step that we did before. We just write it at fc of s comma t, and then sa2 plus te to sa3 plus te3 at a equals b equals 0. And now taking this derivative now is okay, because we see the a2 actually only appears in one entry of this fc, namely in the if this is x0, x1, x2, x3, it's the x2 entry. And then we just apply the rule of derivative that we know. So this is somehow take the inner derivative for a2, this is s. And then we have the chain rule. So somehow we get d of fc divided by d x2. And then we evaluate it at the point a equals b equals 0. So somehow then we get st. And then setting a equals b equals 0 just means that we set 0, 0 in the last coordinates. And so what we see from this is that the s comma t coefficient now exactly gives the first column of this matrix J. And so the first, you see, because this was somehow the derivative with respect to A2 gives the first column. And so these coefficients just give the entries of this column. And the other columns, now you can imagine, you just replace what you take derivative by. So for example, if you take derivative by A3, then you see you get here you still get this S out, and then derivative of fc by x3, the last entry at this point, and then the same thing for the others. So actually, just we get these combinations of the partial derivatives of fc in the last two columns with either s's or t's. Okay, and then the assumption. Let's say this thing was not invertible. Then we need to reach a contradiction. If it was not invertible, then we would find a linear relationship between the columns. In other words, we could write down with some numbers lambda I and mu I, we could write down some linear combination of these things, and we keep it in this kind of polynomial interpretation. So we just sum all of these things up. So we have lambda 2, mu 2, lambda 3, mu 3, and so this is 0. And now, well, to reach a contradiction, let's observe something, namely that both this term here and this term, these are both, I claim, homogeneous degree 3 polynomials in S and T. Because, I mean, FC started out as a degree 3 polynomial homogeneous. If you take a derivative and evaluate it at ST, then, I mean, it is homogeneous degree 2 polynomial, but then you multiply with the homogeneous degree 1 polynomial, and so 1 plus 2 is equal to 3, so you're back to degree 3, like this. And so basically this says this homogeneous polynomial of degree 3 is equal to minus this polynomial of degree 3. And so, and you see it's already partially factored like this. So this decomposes in these two factors, this decomposes in these two factors. And so the claim is this implies that these derivatives here must have a common linear factor, so a common 0. Because, I mean, as polynomials in ST, they must decompose into linear factors. And you see, I mean, this decomposes into 2 linear factors. One of them could be this one, but the other one must be one of the 2 linear factors here. Just there's not enough room left for this here to contain both linear factors here. So there must be one shared between those 2. But having a shared common linear factor just means they have a common 0 at some point s comma t. So in other words, this must have a common 0, and let's call this thing q. So I mean, we see this as a point st inside p1 where they have a common 0, and then I mean this p1 lies in these coordinates like this. This parameterizes this line L. So basically these 2 polynomials have a common 0 at some point in L. And now we want to reach a contradiction. And in fact, the contradiction that we want to reach is there's one assumption which we have not used yet in this entire proof, namely that X is actually a smooth cubic surface. This didn't appear yet, and now is where we use this assumption. So to make a summary where we are so far, we have found this point Q inside this line here, where these 2 derivatives for the last 2 entries of FC at this point vanish. Now the claim is the first 2 partial derivatives also vanish. And this has a separate reason because, well, this line here, this span, is contained in X, which is the vanishing locus of FC. So in other words, FC of S comma T comma 0, 0 vanishes for all S and T. This is the parameterization of this line. And so if we plug it in, we must get 0 for all ST. But then, well, if you take the partial derivatives for S and T now, then you see, well, the first and the second derivative of this must vanish, in particular if we plug in ST equals Q0, Q1. And so this derivative and this thing also vanish. But now we see these things, these derivatives, are exactly the Jacobi matrix of FC. at the point Q. And so by this projective Jacobi criterion, we see that Q is now a singular point of our surface X cut out by this FC. And this gives a contradiction. And so we have reached a contradiction to this assumption that J is not invertible, so J is invertible. And this means that indeed we have this nice picture that this incidence correspondence is locally the graph of such a function. And then next video, we'll see how do we use this to conclude that you get 27 lines over any point in Q.